try to show you how this chapter 4 starts. You know, this might look funny to you, but I want to show you a picture of a graph here. All right. This is some kind of crazy graph, sorry. This is some kind of crazy graph. You guys see it? There's an x-axis, there's a y-axis. I just made this up. But there's some important points here. And so what we did in chapter 3 is we kind of learned how to do derivatives. By the way, chapter 4 is about using derivatives for stuff. I mean, we used them for some stuff, but now we're going to use derivatives for more stuff here in chapter 4. And so one of the things derivatives can help me do is find all these important points. And what do I mean by important points? Do you have any clue what I might be thinking about here? What do you think is important up here? Minimums and maximums. Thank you. Yeah. And maybe I previewed this idea just a little bit in chapter 3. But you're right. I'm looking for these minimums and maximums. And I sort of use the plural, minimums and maximums. I mean, actually, let me just, sorry, take this on up here a little bit. And, you know, overall, on this crazy graph I got going here, overall, is there an overall, and they use the word absolute maximum. Is there some absolute maximum? Well, this arrow keeps going up, and over on the other side, this arrow keeps going up. So I kind of think, no, there is no absolute maximum. There's no absolute maximum. Well, is there some maximum? Is there? I mean, this graph keeps going up. If you think, oh, maybe this is a maximum. It's higher than everybody else, but you can't call that a maximum because is there higher points than that? Yeah. If this keeps going up, there's always higher points. There really is no maximum. I guess you could say, oh, the maximum's infinity, but when that's the case, what we say is there really is no absolute maximum. Hey, is there an absolute minimum? Is there an absolute minimum?
Yes.
Yes.
Yeah, and a lowest place, a lowest y value.
Okay.
Right there, I think. And we say that the absolute minimum here, we say that the minimum is, I'm going to call it -10. I'm just labeling this. The minimum is -10. It occurs at, you know, x equals -3 maybe. You follow me? There is an absolute minimum. It occurs at -3, and what is the minimum y value? -10. Okay, listen, I'm not that interested in, the book talks about absolute max and absolute min a little bit, but I'm more interested in what we call all the relative minimums and relative maximums. So and then sometimes I'll loosely use the word minimums or maximums, and when I do, I mean relative minimums or maximums. Another word they use is local minimums and maximums. In other words, relative to his little neighborhood, look, relative to his little neighborhood, I think this is a max. I mean, I know he's not bigger than, I know there's more maximum places, but relative to his little neighborhood, isn't he sort of king of the hill right here?
Right.
All right, over here, I think, relative to his little neighborhood, he's a maximum. This is sort of a level place here, but I wouldn't call it a min or a max, I don't think. So I think I just found a couple relative maximums. That's the word we use. And then I loosely just say maximums. When I say that, I mean relative maximums. Do you see any relative minimums? Relative to his little neighborhood, I would call this a minimum point. Here's another one. Any other relative minimums? Remember, this guy's kind of funny. He's not really a max or a min. He's funny. Here's another minimum. You guys okay? I mean, I have 3 minimums. Again, one of them was the lowest minimum. So one of them, out of those 3 relative minimums, one of them was the absolute minimum. Out of these 2 relative maximums, we decided there really was no absolute maximum because the graph kept going up, you know. So I'm using the language here. I haven't wrote any definitions down, but I'm using the language of talking about minimums and maximums. And we're really interested in finding these relative minimums and maximums. And then maybe the absolute, but that's less important, really. So what could you tell me? Look, I mean, so I see a bunch of minimums and maximums all over the place here. Anything interesting? Can you maybe identify some characteristics? What happens at these minimums and maximums? I think what happens is the tangent line becomes right, horizontal, or the slope of the tangent line becomes 0, or the tangent line becomes horizontal at these places. When you're at a min or a max, when you're at the bottom of a valley or at the top of a hill, you have these horizontal tangent lines. Your derivative is 0 at these places. Or there's this one. Right here at this one, your derivative is not 0. Your derivative is, it's a sharp point. Yeah. And maybe we remember from chapter 3 that my derivative is undefined. Yeah, my derivative's undefined at that sharp point. All right, so hang on. What am I saying? This is a function called f of x, and I'm saying the derivative is 0. The derivative is 0. Right here, I'm going to say the derivative is undefined. The derivative is 0. Hey, I know this ain't a min or a max. We decided this ain't a min or a max. You hear that? This is not a min or a max. But it's got a derivative that's 0. It's got a derivative that's 0. This one has a derivative that's 0. You guys okay? Are you all right? Or I can see these so clear. These are places where the derivative is 0 or where the derivative is undefined. I have one example of it being undefined. So I guess I'm approaching this kind of from a backward standpoint. I guess I told you we're looking for these important minimums and maximums. And now, what is it that makes it a min or a maximum? And I think the answer is the derivative is 0. Or the derivative is undefined. And that was something we sort of practiced in chapter 3, and maybe you never knew why. Now maybe you know why. In chapter 4, the big theme is to take the derivative and look for when it equals 0 and look for when it's undefined. Why? Because I'm looking for mins and maxes. Did you catch that? That's the big theme. Take the derivative, set it equal to 0, look for when the derivative is 0 or when the derivative is undefined. That's where you'll find mins and maxes. Are they guaranteed to be mins and maxes? No, here's one that's not. But a lot of them are. So they're not guaranteed to be mins and maxes, but the only candidates for mins and maxes are when the derivative is 0 or when the derivative is undefined. But are they guaranteed to be mins and maxes? No, there's some exceptions. This is even another exception right here. I tried to make a place here where the tangent line was actually vertical. And we know that when the tangent line is vertical, that means it's undefined. But so that where the derivative is 0 or where the derivative is undefined, those are the interesting places. And they lead us to mins and maxes. Are they always mins and maxes? No, there's a couple exceptions. They're kind of, that's not a min or a max, that's not a min or a max, right? Okay, so that's the idea. And so really, we kind of start with 4.1, and it starts with this definition. And I'm going to go ahead and tell you, like 2 or 3 weeks from now, probably 3 weeks from now, or whenever we get around to this test, sometimes the very first question on the test is this definition. So I'll go ahead and maybe tell you that now. But I don't know if I'll remember to tell you later. Here's the definition. If f of c is defined, then x equals c is called a critical number. I'm defining the word critical number. It's called a critical number if blank or blank. By the way, these critical numbers are what you see on the board here. These critical numbers are what leads me to mins or maxes. This is a critical number here at this x value, whatever it is. This one is at this x value, whatever it is. Here's one at this x value. Here's one at this x value. Here's a critical number. Here's a critical number. Here's a critical number. Critical numbers are when the derivative at that point is 0 or the derivative at that point is undefined. That's the definition of a critical number. You could almost call it an important number. I mean, if the derivative is 0 or if the derivative is undefined, those are important places. They're probably mins and maxes, although not guaranteed to be mins and maxes. When the derivative is 0, when the derivative is undefined, those are important places. The x values are called critical numbers. And this is the definition of a critical number. Whatever makes the derivative 0 or whatever makes the derivative undefined. That's not too hard. Like I said, what I usually do on the chapter 4 test, first question, this is on there. It has these 2 blanks. You fill in the blanks. And what's kind of amazing is 3 or 4 weeks from now, people have a hard time with that. They don't, I don't know why. They're not sure how to write mathematics, I guess. They're not sure how to write the derivative at that point is 0 or the derivative at that point is undefined. But that's how you write it. So this function, this function visually, I see tons of critical numbers. 1, 2, 3. I mean, they're all these x values is what they are. If you want to call them critical points, then maybe I just want to say something. Critical numbers are these x values, I think. If you use the word critical points, what do you think I mean now? Yeah, thank you. Because it's a point now, it's more of an x and a y value. Right. And that would be these points. And there's a bunch of them on this particular weird function. And a bunch of them are mins and maxes, but there are a couple of exceptions that aren't mins and maxes. Yeah, cool. So, watch this. Can you find a critical number? Watch this. All right, can you find critical numbers? Find the critical numbers. All right, you're right. It's not too hard, although, right, it's not too hard. The derivative is easy. Maybe you might see some easier derivatives this chapter. We'll see. The derivative is easy. Can you help me? 15x squared minus 13. Good job. So there's the derivative, which is the slope of the tangent line in general at any point. I guess I'm looking for the places where this derivative might be 0 or undefined. Let me just ask you, where is this undefined? Never. I make a habit of asking that because a critical number is where it's undefined or where it's 0. But where is this undefined? Never, thank you. But where is it 0? That's another question. We set it equal to 0, and we try to solve for x. You know, I didn't really try to make this nice. It's not that nice, but it's not that bad. It's 13/15. Do you guys agree? I mean, actually, x squared is 13/15. So what's x? Plus or minus the square root of 13/15. That was my number, man, when I played quarterback. I'm just kidding. On the tennis team, that was my, no, I'm just kidding. Cool, those are critical numbers. Those are critical numbers. And they're probably mins and maxes. Well, one's probably a min, maybe the other's a max, maybe they're 2 maxes, maybe they're 2 mins. Would you like to know what they are? Are you curious? They're critical numbers. We found the critical numbers. Well, get rid of this.
Yeah, I think you'd have to plug it in for the function, yep.
All right. All right, bear with me here. Hang on. I'm going to get back to that question. Hang on a second. Look at this. All right, so here's a function. Here's something here. This is a critical number, and it's a max. Do you agree? Okay, it's a place where the derivative is 0, so it's a critical number. You look at the picture, it's easily called a max. Check this out. Check this out, please. Check this out. Check this out. So on this side, what's the slope of the tangent line? What's the slope of the tangent line? What's the slope of the tangent line? I don't really care what it is, but it is kind of slanting that way. Can I say that the slope is positive?
Yes.
The slope is positive. All right. So but it looks like it might be getting less. Look, it was kind of steep. It was positive and steep, but now it's getting less steep, less steep, less steep. So I think it's getting less. In fact, when it gets to the top, what's the slope? 0. And then when you go around to the other side, what's the slope?
Negative.
It becomes negative, doesn't it? And you can see this. This is very visual. Maybe some of this chapter can get kind of visual. All right, hang on. What did I just say? That the slope, the derivative, is positive. And right at the top, the derivative was 0. And over here, the derivative was negative. Different way to say that. You can say the derivative is greater than 0. The derivative is less than 0. Right? So if your derivative is positive, well, I guess we never said this in chapter 3. This is important. And this picture says it. When the derivative is positive, your tangent line slants this way. If your tangent line slants this way, your function is increasing.
Right.
Does it look like that?
Yes.
And by the way, increasing and decreasing only work if we all agree to read left to right. So reading left to right, this function is increasing. And when the derivative is positive, the function is increasing. When the derivative is negative, over here on this side, the tangent line slants, the derivative is negative. And when the derivative is negative, the function is decreasing. If a function goes from increasing to decreasing, what must happen in the middle? If it goes from increasing to decreasing, it must hit a max. What if it goes from decreasing to increasing? It must hit a min. This is all nice and logical, actually. You with me? Good. I'm glad you're nodding. You seem to understand me. All right, so now let me show you what I'm going to do with that idea. I'm trying to decide what I found these critical numbers, and I'm trying to decide they're good candidates to be mins and maxes, is what they are. And I'm trying to decide, how do I know if they're a min or a max? Well, I'm taking you up to 4-3 now. Okay, listen, I'm taking you into 4-3 now. And in 4.3, I'm going to teach you what's called the first derivative test. First derivative test. First, let me just tell you what it is. It's a test to decide if your critical numbers are minimums, maxes, or neither. That's what this first derivative test is for. It'll help you decide whether those critical numbers you found are mins or maxes or neither. Check it out. Here's how you do it. You ready? What do you do? What do you do? What do you do? I'm going to do it. Here's how you do a first derivative test. You draw a number line, and this number line represents x values. And then I'm going to label my number line, my first derivative, f prime. And I'm going to put those critical numbers that I found on here. Now those are kind of nasty critical numbers, but they are little numbers. They're little 0.9s or 0.8s or something. The square root of 13/15. One of them is here, the positive square root of 13/15. The other one's here, the negative square root of 13/15. So you guys okay? I mean, I'm sorry, they're nasty little numbers, but that doesn't matter. They're numbers. And they could be ones, they could be twos. It just doesn't matter, right? It doesn't matter. They're numbers. At some point, you're mature, and numbers are numbers. But roughly, what are they? I do need to know what they are. Am I right?
0.931.
0.931. That's even after you took the square root.
Yeah.
Yeah, 0.9. Okay, so roughly, this is a 0.931. This is a negative 0.931. Okay. All right, so what is the derivative doing at those points? What is the derivative doing at those points? The derivative is 0 at those points. They're critical numbers. I mean, that's how we found them. The derivative is 0 at those points. They're probably mins or maxes. What is the derivative doing in between those points? That's what I want to test. So watch this. I'm going to test in between here. What's a good test number in between here? 0. I'm going to do, little 0 is going to be a test number. Look, I kind of big and bold these guys. These are my critical numbers, but I'm going to pick test numbers around here. So what am I going to do with this 0? I'm going to plug it in the derivative. Watch this. I'm going to plug this into the derivative. Where's my derivative?
15 minus.
Oh, yeah. I'm going to plug this in my derivative, and what do I get? Negative 13?
Yeah.
I get negative 13. Okay, listen, I don't really care that it's 13. The point is, it's negative. My derivative is negative. What did we just learn? When the derivative is negative, the function is decreasing. Big idea. All right, hold on. Here's how I make little notes. I say, I tested this in the derivative. I found out it's negative. I make little negative marks there. But then I want to say that the function is decreasing. Left to right, that looks like this. My function is decreasing. And I draw this little note here. See this little note, this little arrow? My function is decreasing. In this region of the graph of the function, which I haven't bothered to graph. Hey, let's test something out here. Can you pick any number you want out here? Any number you want.
1.
1 would work. 2, 3, 4, 10, anything would work. Sure. We'll try 1. I'm going to plug in a little 1 for a test number. I'm plugging 1 into the derivative to see if the derivative is positive or negative. This is going to tell me a lot. I'm plugging 1 into the derivative. It's easy. It's 15 minus 13. It's 2. It's positive 2. The point is it's positive. The truth is any number out here would come out positive. This is positive. What do we know when the derivative is positive?
It's increasing.
The function is increasing. The function is increasing. Dude, check this out. We just learned something. This critical number showed up in between decreasing and increasing. If the function is decreasing and then increasing, this critical number must be, the picture shows you, this guy must be a min. Whew, I'm going to circle him and call him a min. This other one's probably a max. Let's just check it though. Pick any number out here for a test number.
-1.
All right, -1. I'm plugging it into, this came out to 2. I'm plugging it into the derivative. This is just, these are the little test numbers here. I'm plugging -1 into the derivative. Where's the derivative? I'm plugging -1 into the derivative. 15 minus 13, that's positive. That's a +2. So it came out positive. I label it with little positive signs, but what that really tells me is that the function is increasing. I label it with that little picture. I'm writing these words, which I usually don't do, but this is the first problem we're doing here, so I'm over teaching like I do. The function's increasing, and then it's decreasing around this critical number. Remember, he was the critical number. It's increasing and then decreasing. This has to be a max. Yep. Yeah, that's awesome. That's awesome. So first thing I did was say, find your critical numbers. And in 4.1, you got a lot of those. Find the critical numbers, find the critical numbers. And you don't really start testing them too much yet. Until you get to 4.3 and you do this thing. This is what you do with your critical numbers. You put them on a number line and you do this process. This whole process, this whole thing here is what I call a first derivative test. Take your critical numbers, put them on a number line, test everything in between, draw your conclusions. I mean, this process, you could do it your way, but you can do it my way. I mean, again, I'm analyzing the hell out of this function. I'm analyzing the heck out of the derivative, which tells me a lot about the function. That's really what's going on. I'm analyzing this derivative. I know when the derivative is positive, I know when the derivative is negative, I know when the derivative was 0. I found critical numbers, I know about increasing and decreasing, therefore I... Right.
When you plugged in -1 as a test number, why is that a max?
Well, so when I plug -1 in for a test number, I got a +2.
Right.
So now listen to me, -1 is not a max. These little guys are test numbers. These little guys ain't mins or maxes. The mins and maxes are these points. These critical numbers. See these critical numbers?
Right.
One of them's a min, one of them's a max. And how did I figure out who was a min and who was a max? I tested around those critical numbers.
Okay.
You know, when you put two critical numbers on a number line, that leaves you 3 regions to test. Yeah. And I tested this region, and this region. I tested all 3 regions, and I found out that the function was increasing, decreasing, and increasing. Well, that led to a max and a min. Do you see that visually? Do you see that? Increasing and decreasing, this has to be a max. Decreasing, increasing, this has to be a min. There's times, I mean, here's just, you know, what is this? This is a made-up first derivative test. I mean, you could have a bunch of critical numbers. You could test this was increasing. You find out this is still increasing. This is decreasing. This is decreasing. I mean, these are 3 critical numbers, but what's the conclusion? Is he a min or a max? Yeah, he's not either one. It increases and then it keeps increasing. I'm not sure what's going on there, but it ain't a min or a max. To be a min or a max, you got to change. You got to go from increasing to decreasing, or you got to go from decreasing to increasing. That's what makes you a min or a max, right? This guy's a max, right? This guy's a neither, right? So the first derivative test tells us whether we're mins, maxes, or neither. So this example has a couple of neithers up here. You know, after it's all over, and it is all over, what did we do with this function? We found its critical numbers and we tested them to try to find out who's a min or a max. after that all over, you know what? You got a good, you got a good looking graph of this thing, or you could get yourself a good looking graph without your graphing calculator. I mean, when we hit chapter 4, it's time to, here, pass around this garbage can. It's time to just get rid of these. I'm kind of kidding. But I'm sort of, I mean, really, with this calculus knowledge here, analyzing the derivative can tell me so much about the graph of the function. And there's more to say, but I can't go too fast. Like, look at this. Let me see. Can I plot these points? These points suck, don't they? The square root of 13/15. I mean, if I actually wanted to plot this on a graph, how do I plot it? What does that mean? What do I mean by plot it? Like, go back to the original function and plug it in, which does kind of suck. You could just estimate it for me with a 0.931. Can you help me? Cubic times 5. I'm gonna say -7. It was approximately a 0.931. I'm going to say it's at -7. Am I right? -8.9 something? Okay. So she said -8.9 something. So I was sort of close. So that's that point. When you plug in 0.931, you get -8.9. What happens when you plug in -0.931? I think you probably get about +8.9. I could be wrong. What happens when you plug in this guy? Am I right? I'm plotting this. He's a max. I think I got the right y value, but I'm totally just, how do I get this y value? I plug it in the function. I mean, I admit it kind of sucks, but so what? Plug it in and do it, and it's roughly 8.9, I think. And when I plug in the other one, it's roughly -8.9. I plotted these two important points. I think this one's a max and this one's a min, according to my work here. And now, can I just like connect the dots? I mean, look, I can read this number line. I know what's going on. To the left of this, my function is increasing. So it's got to be increasing until it hits this max. What does it do after it hits this max? It starts to decrease. Then it hits this place. What does it do after it hits this place? Then it increases. So it increases, it decreases, it increases. In between there, it hit a max, it hit a min. I mean, this is a typical kind of cubic function. A typical cubic function probably has a min and a max, kind of like that. They don't always, but a lot of them do. All right, that's pretty cool, you guys. Now, that's good stuff. That's really good stuff. I need to really back up, though, to do the 4-1 homework. I mean, I like things to flow, and this flowed. I don't know if you caught it, but this flowed. I mean, this is what we do. We find critical numbers, and we test them on a first derivative test. But I had to leap up into 4-3 to help you with that. In 4-1, the book doesn't quite get there yet. In 4-1, they're doing some funny things. You know what they do? They make me look for mins and maxes, but they make me work on a closed interval. Right. It's kind of weird. It's kind of like this. Like if I was looking for mins and maxes on this function, but I was only working from here to here. What the hell does that mean? Look. Find the mins and maxes here. Well, on a closed interval, that means that the rest of this graph wouldn't even exist here. You with me? They want me to only look from here to here. Where's this? Where's this? This is here. So that means the rest of this graph doesn't even exist. So I'm working from here to here, and I'm trying to find mins and maxes. I'm working on a closed interval. It's a little strange, but guess what? Guess who's still a candidate to be a min or a max? The critical number is still a good candidate to be a min or a max. It is a min, by the way. It looks like it's still a min. Even if you're working on this thing, I would call that a min. But you know what they're going to call a max? Maybe you know. Can you tell? Who are working from here to here? What are they going to call a max?
The end point on the right.
This point over here, they're going to call this a max. And we all know that in the scope of the whole function, it wasn't a max. But when we're working on this closed interval, we're going to call this a max. But this guy still came out to be my min. It's a little weird. I need to do an example, but this was a decent preview of it. Yes?
So when it comes to quiz or test time, the way the book does it, you're not going to require us to
Well,
do a quiz.
I don't know about that. I'm not sure yet. I'm a little bit not sure yet. I mean, so in 4.1, to practice some homework, how does it show up on quiz or test time? I'm not sure yet. But in 4.1, to practice some homework, they ease you in.
So you want us to practice it the way the book shows us?
Well, hang on. The big theme of this chapter is going to do this. 4.1, find your critical numbers. 4.3, do a first derivative test. But before I get here, there's some stuff I'm doing first. And I'm working on a closed interval. Where I still find, let's do an example. But you're worried about quiz or test, and I just don't know what to tell you yet. This is quiz or test, definitely. Is this quiz or test? Maybe in some, yeah, maybe. But not, there might be 5 of these and 1 of these or something, so.
So if you have a closed interval, you should check the end.
Well, right. So watch, so here's the strategy in 4.1. And let's do, let's just do a problem. I'll do, 2x cubed minus 6x. So here's a function. 2x cubed minus 6x. But now look what they're doing to me. They make me work on this closed interval from 0 to 3. Closed interval. But the directions say, this happens to be in 4.1 and it happens to be number 26. By the way, let me just say something else here, I guess. Let me say something else here. They use the word extrema. Extrema, that's plural for extremum. It's sort of a one good word that encompasses both mins and maxes. Do you agree?
Right.
Okay. So they say find the extrema. That means find all the mins and maxes. Right. So, on this closed interval. Okay. Well, we know that a good candidate for mins and maxes is critical numbers. Dude, you need critical numbers first. So let's find critical numbers. How do you find critical numbers? Take the derivative. 6x squared minus 6. Do you agree?
Yeah, right.
And when does it equal 0? Right. Let me just pause and ask this stupid question. When is it undefined?
Never.
Never. Why did I even ask that? Well, because to be a critical number, it could be where it's where it's undefined or where it's 0. A lot of them are never undefined, so we get out of the habit of asking that. I want to make sure you're still worried about that. But in this case, this guy's never undefined, but when is it 0? Okay, when is it 0? This is easy, right? Move the 6 over maybe, however you do it. Divide by 6, I get x squared equals 1. X is?
Plus or minus 1.
Plus or minus 1. I got 2 critical numbers. Maybe one's a min, maybe one's a max. Hold on, I'm doing this funny thing where I'm working on this closed interval. So if I'm only working on the closed interval 0 to 3, then I guess I should toss out one of these.
Negative 1.
Yeah, the negative 1 doesn't live in this interval from 0 to 3. I guess I'll only use x equals 1 because I'm working on this interval 0 to 3. And you know what I could do? I could do a first derivative test, but my number line wouldn't go forever. What would my number line do? It'd go from 0 to 3. And I could just work on from 0 to 3 and kind of analyze a first derivative test. But that ain't what they tell me here. Hang on. That ain't what they teach me to do. What they teach me to do is I'm looking for a min or a max. And it could happen at the critical numbers, but it could also happen on the damn endpoints. When you're working on a closed interval, I just erased my evidence of that. But I showed you that a second ago. When you're working on a closed interval, your min or your max could happen at the endpoints or at any critical numbers that live in between. So I simply do this. To figure out who's a min or a max, I figure out who has the highest y value and who has the lowest y value. How do I find y values? Plug them into the original function. So I try to find f of 0. I try to find f of 1. That was the critical number I had. And I try to find f of 3. The mins and maxes could occur at the critical numbers you find or at the endpoints of the interval. So here I go. Just plugging these in to find, let's see, what happens when you plug in a 0? Y value of 0. What happens when you plug in a 1? -4. Y value of -4. In the original function now, I was doing something different a few minutes ago. I was testing the derivative. I'm just finding y values. Original function, trying to find y values, see who's bigger or littler. Plug in a 3.
36.
36. All right. Who's a min and who's a max? I think I could ask my kindergartner this, maybe. Maybe not. Plus he's already in 2nd grade, never mind. That's a min, I think. Is that the lowest y value you see?
Yeah. So
there's a min that occurs at this place. And I guess we would call him a max. There's a max that occurs at this place. It's a little strange. Working on a closed interval. Again, one more time here. This is a function. I think it kind of looks like this. We were working from 0 to 3 though. Hey, we were working from 0 to 3. So let me erase that. Let me erase that. And from 0 to 3, we found a max at 3. We had a max of 36. And at 1, we had a min of -4. Are you guys following me? I mean, there's the picture of what we just discussed. I don't need the picture. I did fine without the picture, to tell you the truth. But I'm just trying to show you and confirm to you what happened.
So even though 3 wasn't a critical number, we still count as a max?
Yes. And that never happens anywhere else in this chapter. But it happens why does that happen? He said even though 3 was not a critical number, we're still going to call it a max. Even though 3 was not a critical number, we're going to call it a max. And yes, but that's a temporary little idea because we're working on this closed interval. We're working, and so a min or a max can occur at the endpoints of a closed interval, right? So it's kind of this funny little exception. As soon as we move past 4.1, we don't really talk like this. We talk more like this.
Okay. But that's going to be.
Let's do another one. Look at this. Can you find this guy's critical number? Find that critical number. Here's another one. Here's another one. Find this guy's critical number. All right, so I'm stepping it up a notch. I'm stepping it up a notch. I'm gonna hit